Hi all. This video is about a paper titled An Evolutionary Tuned Driving System for Virtual Car Racing Games, the Autopia Driver. So what this paper is about is to implement car racing driver may by implemented by means of hand designed driving heuristics, but some of the features designed for this car racing driver is optimized by means of a genetic algorithms. This evolutionary based control systems for designing this car racing driver had participated in 2010 simulator car racing championships, and finally it ended up winning the competition. So we see that today's games have become a test bed for the study of a computational intelligence. So the traditional games like having some pieces and cards have discrete interactions during the game, and those end up in combinatorically quickly enormous possibilities to choose the optimal decisions. And this complex decision making process are very much required to play such games at a high level. So this in these last few decades, these algorithms have phenomenally increases in to have a test bed in playing a computer games. So one among the computer game becoming a car racing, and it has become a test domain for a method of applying artificial and computational intelligence to design autonomous driving techniques. Therefore, this designed computational intelligence techniques uh, to implemented in the car racing games have become a test bed for cross fertilizations between research from the robotics and the artificial intelligence. So, for example, the goal in racing game is to guide some sort of vehicles towards a goal efficiently, controlling the dynamics of the vehicles, and as well as to avoid the collisions and respect the traffic behaviors, and also making competitions with the other drivers to win the race. So in this paper they have used open source car racing simulator called talks to test their algorithms related to the computational intelligence. In this talks, usually the tracks models are not given explicitly. They have to be learned through the partially sensory data, which we will be describing in the section 2. So the past few years, these car racing games have become a test bed again to implement many computational intelligence algorithms based on fuzzy logics. Some of the learning techniques has come from reinforcement learning, and researchers has put their much effort in testing their techniques in this driving along this track, particularly using this talk simulator. So this one of the this author says is about they have put their effort in involved in competitions like simulator car racing competition in the last 3 years, and they claim that they have used computationally simplistic car racing modules, and even though it seems to be a simplistic car racing modules, it claimed to win those competitions based on the talks environment. So again, what we described earlier is there are computational intelligence algorithms being developed, and that has to be uh, tested. And that test bed is one of the test bed is becoming the car racing games. And the car racing games, in the one of the open source is Talk Simulator, and they have arranging a different competitions. And these authors have participated in different competitions, and one and different competition based on a simplistic and heuristic based computational intelligence algorithms. So some of the other techniques are related to the fuzzy logic and other reinforcement learning, but here they have used fuzzy logic and also evolutionary strategies called genetic programming. So we all know that genetic programming is a search algorithms, and the mechanism of the search algorithm is like selecting among the different species which survive, sorry, which which survive the fittest one will be chosen as a selected candidates, and that will be utilized for the fitted we utilize the fitted candidates for the final solutions. So here a new set of individuals, as mentioned earlier, has been chosen, and some of them exploration and exploitations here to be applied, like randomly selecting some of the things, and the best chosen from the previous one will be retained back. And it's not purely a simple random walk, but it has some efficient exploitations using the previous historical information to search for the new points. Here, the primary objective of this paper, they say, is twofold. One is to design, implement, and test a complete driving architecture for autonomous driving in racing conditions. And the second would be to construct an efficient and also a simplistic, understandable controller for the car robots. And those driving architectures and the controllers will be based on the fuzzy based module, and some of those modules will be tuned based on the genetic algorithms. And the sections are divided into 5 sections. The section 2 describe about the racing environment, the talks environment, and the talk simulator itself. Section 3 describes about the fuzzy logic driving architectures implemented in this paper and how they are optimized. Section 4 presents how this fuzzy logic genetic optimization process implemented is much better than the naive fuzzy logic without utilizing the optimization process. And also it compares with the other competitors and to see how far this is performing much better than the other competitors, and the final experimental results related to the competitions will be present in the section 5. So we know that the tax environment is based on open racing car simulator. It's a C++ code based, and each vehicle will be a drive robot, and uh, it will work through kind of a local server client mechanism. So that's what this says here. And track informations will not be given directly, but through some kind of proximity sensors based on two types of classes. One is the information about the track will be given based on the measurement distance to track borders. That what does that means here, for example, if the for the present positions, and there will be many sensory informations along the different angles from -degree to +90 degree. And if the sensory data information is 200 meter, it is mean unobstructed, and how much distance on each sensory data travels will determine you the local informations about the track. And also the opponents, how there also will be a sensory information how throughout the 360 degree, and how far that information given for the particular direction, like 200 meter will be a completely free, and how much distance is reducing from the 200 meter will say you that how much close that opponents are near to that particular directions. So these are the information. Apart from these informations, they will be giving you some other details about the location of the vehicle, like how much it deviates from the present track. Like -1 will be from the far left, and +1 will be from the far right of the track, and how much orientations along the track, and how much distance that it has traveled from the starting line. So these are some of the information they will be giving you along with that sensory informations. And also they will give you that how if you are keep the vehicle being colliding, and how much the damage it has happened for the vehicle before that 100% is been retired from the race and finishing in the last positions. There are four outputs from these controllers for these sensory inputs. One is the gear shifting. From -1 is for reverse gear. From 0 to 1 to 6 will be for the different gears based on the different RPM performance. And the steering value will be from -1 to plus right for the full right and full left. And throttle and brake will be from 0 to 1 calibrated, but we can put it as a one value between minus 1 to 1. And the negative values will be for brake and positive values will be for the throttle accelerations. So on the driving architecture has to give what gear value, what pedal value, what steering value, and how the situations if this block and how to come up from that, and what would be the if there is an opponent, how to modify the steering and pedal value based on the opponent conditions. And these algorithms have some kind of parameters and how those parameters can be tuned during the learning module. So there is two level of control. One is low level control is like gear, pedal, steering, and the informations are learned locally at every time. And module 5 to since a high level that would be uh, determined determined from the separate process from the low level controller. So yeah, these are the simplistic setup, and the gear control is something. This is the equation that will decide the gear whether to go for a positive and what levels 1, 2, 3, 4 based on the RPM. If, for each gear, there will be a threshold of minimum and maximum. If that is been in that threshold, then that gear will be utilized, and if it goes to the again the RPM keep shifting, then that gear level will be shifted based on that threshold level. So this is mechanically designed, and these are the some of the gear ratios values. Based on this, the design and the gear will be shifted, and pedal control will be like a brake and throttle control, and that will be designed by these equations. And how far this current speed is deviated from the target speed, that will be gives you a pedal. If it is very low, then it will go for the target speed is based on this. If based on this difference, there will be a pedal or brake based on this equation. How this target speed is computed will be given in the later module. And the steering control is same based on the equation 3. It is an empirical formula. It has like alpha, alpha minus a set of alpha values and set of this st1 to st5 parameters. And this alpha value is a key one. What does this mean by alpha? And alpha minus 1, alpha minus 2, alpha minus 3, alpha plus 1, alpha plus 2, and alpha plus 3, t minus 1, t minus 2, t minus 3, t plus 1, t plus 2, t plus 3. So what are these values can be easily identified through this uh, diagram. So alpha is the direction where it can travel the much longer distance. So that will be chosen as alpha, and every degrees in the alpha will give you alpha minus 1, alpha minus 2, alpha minus 3 in the left direction, and alpha plus 1, alpha plus 2 alpha in the right directions. And same thing like t minus 1, t minus 2, t minus 3 in the left, and t plus 2. So how those alpha values will be chosen, and how much distance that has been chosen will based upon this alpha value, which is the largest distance that it can be traveled. So those values will be substituted here, and those values will be multiplied by these tuning parameters. With these tuning parameters will be decided by will be designed by a genetic algorithm, which will be explained later. And similarly, the target speed, what target speed it has to go for that particular occasion, is also similarly based on the thing that we have discussed earlier. That alpha, this based on this t0, t1, t0 value. T0 is something like the maximum distance that it can be traveled. Yeah, similar to this things. Then how much it can travel the maximum distance, and that left side will be minus 10, minus 2, minus 20, like that, and the right side will be 10, 20, something like that. So these values will be, this value will give you an accuracy, and this will be utilized, these values are utilized for the smoothing to have the proper target speed, and as well as for the proper steering value. So this three will equation three is something like to move the steering proportionally in the direction of the largest sensor measurements. And there is also another one fifth parameter ST5 will driving along the straight line segments, and there will be a value to determine whether we are going straight or not. If alpha is zero, then it means that it's going straight. If alpha is non-zero, then we are going a curvature, and then that equations will be invoked. And there are also based on the damage situation, the target speed alone has should not be implemented, because we if we are more damaged, then it would be highly insensitive and dangerous to use that target speed, as we are almost in a highly damaged, then we may end up in further damages, then we'll end up in going out of the game. So that has to be scaled properly using these equations. So this is for the open things, that steering control and the target speed. Based on the target speed, how that speed is compared using the exponential equations. But once we have this detected obstacle, then that computed that steering and the speed value has to be modified in order to avoid these collisions. So that will be based on these empirical relations. Once we have the obstacles along these positive directions, then we have to steer based on these values. Based on this value to move further along the free distance. For example, if there is a steering, if there is an opponent direct along the left side, then we have to steer more towards the right based on this empirical relations. Similarly, if you have some kind of opponents in the left side along uh, uh, this zone of degrees, then we have to based on using this formula to steer the right. Similarly, then whole deviating from the right. This applies also to the mirror rules. Like if these rules have been designed for how to move to the right if there are vehicles located on the left side at different degrees, and similarly if the vehicles are located at the right side, how to move to how to steer towards the left based on the different locations of the opponents. So this has been clearly defined in this figure. If there is a vehicle here, then we have to make this has been rightly slightly been the right side, so we have to steer to the left to this amount, and we make collision free uh, forward directions, forward movement. Same thing, that how the speed also should be adapted, how close this how close this opponent is in being in front, and on which alignment this is in front, and how much speed we are trying. Based on this conditions, then the speed has to be adapted, whether the speed, how much brake has to be put, whether or how much speed has to be adapted based on this logical physiologic conditions. So this truck management and this is not a main process. The main process is how this genetic algorithm being utilized in the fuzzy logic to tune those parameters. So that is being given in this fourth sections. That among those gear control, steering control, speed control, and target speed control, different we have discussed almost like 5 modules. Only the steering control and the target speed modules have some parameters like st1 to st5, and ts1 to ts5. These are being augmented as a single 10 dimensional vector, and the genetic algorithm is schema is utilized to identify the best parameters. First, initially n 20 individuals are taken as a populations, and they have been randomly initialized from -5 to +5. And once these things are been there are 4 processes. We know that selection, crossover, mutation, and replacement being applied repeatedly for 100 generations, and from that the final tuned parameter will be utilized for the racing in the Autopia. So these 9 pairs will be taken, and it will be crossover and mutated, and to try to get the one, and the 2 from the previous generation will be retained. The best one will be retained, and this will crossover and mutations will have some randomizations to choose which location that has to be mutated will be uniformly selected from 1 to 10. and based on this criteria there will be a mutation crossover will be done, and the survival of the fittest will be fitted, and those values will be utilized for the optimization for the final track conditions. How this been selected among this one is how which are the things has to be written, which are the things has to be omitted is based on the survival of the fittest. That survival of the fittest will be something like based on some kind of simulations. So each individual will be utilized in a car racing conditions in a oval track, four different oval tracks for the different time steps, and which one is performing well without any collisions or without any going off track, or how much maximum distance is covered without any particular damage will be retained, and others will be discarded, and this will be continuing for a particular number of generations, and the final output would be utilized in the car racing conditions. The final steering values are being inputted into that previous mentioned equations, and this is the final equation that will be utilized for the car racing conditions: 0.21, 1.56, 0.68, 0.53. And for the straight conditions, these are the conditions that has to be utilized. And the ST5 parameters, somehow it has to be mentioned, I couldn't able to find out. And same thing, these TS parameters are being improvised here, and these 8 and 9 equations will be utilized for the final competitions. So once this been selected, and there are three level of comparison. One thing is this same on different these are the different tracks. The first comparison is between the base parameter and these tuned parameters, how they could able to perform, and that comparison chart is mentioned in this one, and we could see that the green is the tuned one and the red is the base one. So green could able to perform much better than the tuned one. And the second level of comparison is between same thing in the track condition, laboratory conditions, where there are default models, bots like 1 to 7 from Bernice, developed from the Bernard Weyman, uh, who develop the talk projects, have those default bots, and those were picked from 1 to 7, and this Autopia is been competited with those in open race condition, and also with the together opponents conditions. In open race conditions, these are 12 tracks that has been tested, and how many seconds it took compared to the other models. The least one is the best one. So we could see that this the Autopia seems to be much lesser time compared to the all other models. So even, and also in racing conditions, it could come first in most of the things, and with less number of collisions, and more number of overtakings happen during these conditions. This is what position it comes with, all along with that 7 default robot. And one important thing is this Autopia doesn't know the existing track conditions, but all those 7s uh, have more additional information compared to Autopia, that they know the existing conditions. Again, this could say that this tuned fuzzy logic based controller can able to perform well with the controllers which have been developed by the talks simulator person itself, and where that talks bot could able to know the track information ahead compared to the Autopia. Then and some of the results has been shown that they participated in the 2010 simulator car racing championship, and different setup has been during the warm-up conditions and the qualifying stage and the final races. This will determine how this warm-up and qualifying stage will determine what is the best first 8 bots will be utilized for the final races. And when it is one of the 8 among these 8 one, Autopia is one among the one chosen, and they have different tracking conditions called gecko, WC, and dirt tracks, and these results have been summarized here. Among this, Autopia scored a higher score in Gecko, and it came third in WCCA, and the dirt tracks it came again first. With this summary, Autopia was able to run faster than other controllers on all of the tracks, and and it could say that among the overall points, it could take the final result was first got two in the first two places and third in the last two places, and it becomes the winning champions overall with the 17 points of difference from the second classified GoPostar. So Autopia was the only controller able to beat those presented by the organization of the championships. So in this what is the crux of this paper is to that the racing simulators, these games can be a test bed for testing the robotics as well as developing the computational intelligence algorithms. So that is one of the crux that this paper has been chosen to provide in this video, and it is very beautifully written. And please, if you have a time, please go through this paper. Thank you.